All right, let's talk about something that's, at the very core of pretty much any application you can think of. It's data foundation. We're going to dive into how to build a solid blueprint for a database that's not just efficient and reliable, but one that's actually built to grow. So let's jump right in. Have you ever tried to build something, maybe even something simple like IKEA furniture without the instructions? It's chaos, right? Now imagine trying to build an entire house without a blueprint. It'd be a disaster, wasteful, unstable, just a mess. Well, that's exactly what happens when you try to build an application without a proper plan for your data. And hey, take a look at this. This is what that chaos actually looks like in the wild. We've got this single, giant, messy table. See how the user's name and address are just copied over and over again for every single order they make? So what happens if that user moves? Well, you have to hunt down and update their address in who knows how many places. That is a recipe for disaster. We're talking errors, terrible performance, and just a massive headache waiting to happen. So to avoid that nightmare scenario, you need a blueprint. Simple as that. And in our world, in the world of data, we call that blueprint a data model. It's not just a good idea, it is the absolute essential first step to designing a database that's structured, clean, and optimized. Okay, so how do we actually go about creating this data blueprint? Well, it's not like you just scribble something on a napkin. It's a really structured process, a journey that takes you from a big, high-level idea all the way down to a concrete, ready-to-build plan. And that journey happens in three main stages. Think of it this way. First, there's the conceptual model. This is the 30,000-foot view where you're just capturing the big picture business needs. Then, you get more specific with the logical model. This is where you start mapping out the detailed structure of the data itself. And finally, you have the physical model. This is where the rubber meets the road. You're figuring out the nitty-gritty of the actual database implementation, thinking about things like performance and storage. So, every blueprint has its basic building blocks, right? For us, the most important ones are called entities. An entity is just a fancy word for any real-world thing we care about and want to keep track of. So if we're building an e-commerce site, our big entities are going to be things like users, orders, and products. Makes sense, right? And of course, each of those entities has details about it. We call those attributes. They're just the specific pieces of info that describe the entity. So for our user entity, the attributes would be things like their name, their email address. You get the picture. These are the details that actually make our model useful. But here's where the real magic happens. It's not just about the entities and their attributes. It's about how they connect to each other. We call these connections relationships. For example, you have a one-to-many relationship. One single user can have, well, many orders. Or you might have a many-to-many relationship. A single order can have many products, and a single product can be in many different orders. These connections, this is truly the heart and soul of a relational database. All right, so we've got our basic blueprint sketched out. We've got our entities, our attributes, our relationships. But we're not done yet. Now it's time to refine it, to make it better. And we do this with a process called normalization. You can think of this as the quality control phase, the step that really makes our design super efficient and basically bulletproof. When you boil it all down, normalization is really about two key things: getting rid of repetitive, redundant data, and making sure the data you do have is trustworthy and consistent. It's the secret sauce that takes a pretty good design and turns it into a great one. So, normalization isn't just a vague idea, it actually follows a clear set of rules, or what we call forms. Now, there are several of them, but we're going to focus on the first three, because honestly, these solve the vast majority of problems you'll ever run into. We're going to tackle them one by one and watch our data structure get cleaner with each step. Okay, rule number one, first normal form, or 1NF. This one is super straightforward. It's all about atomicity. All that means is that every single cell in your table should hold one, and only one, indivisible piece of information. So you can't have a cell that says math, science. No way. Instead, you'd split that into two separate rows, one for math and one for science. And why does this matter? Well, now you can actually search for everyone taking math without having to do some crazy text parsing gymnastics. It makes your data instantly clean and searchable. It sounds simple, but trust me, it's incredibly powerful. All right, on to second normal form, or 2NF. Now, this rule really comes into play when you have what's called a composite key, basically a primary key made up of two or more columns. In this example, it's the combination of student ID and course ID. So 2NF says that every other piece of data in that row has to depend on the whole key, not just a piece of it. But take a look here, the course name. Does that depend on the student? No, it only depends on the course ID. That's what we call a partial dependency, and it's a problem. So how do we fix it? Simple. We split the table. We pull that information out and create a brand new courses table that just holds the course ID and the course name. This is so important, because think about it. If the name of a course changes, now you only have to update it in one place, not for every single student who's ever taken it. Boom. The partial dependency is gone and our data just became a whole lot more reliable. Okay, last one for now. Third normal form, or 3NF. This one is all about getting rid of something called transitive dependencies. The best way to think about it is like that old game of telephone. Look at this table. The student ID tells you the course. The course tells you the instructor's phone number. So the instructor's phone number depends on the student, but only indirectly through the course. It's a dependency on a non-key attribute. That's a transitive dependency, and it's another source of problems. And you can probably guess the solution by now, can't you? We split the table again. We just create a separate instructors table to hold that information. And the payoff is huge and immediately obvious. If an instructor gets a new phone number, you change it in exactly one spot, the instructors table, and that update is instantly correct for everyone, everywhere. No more inconsistencies. Okay, so we've got our refined blueprint. It's been normalized, it's clean, it's efficient. Now for the fun part. How do we actually build this thing? Let's talk about the key tools that turn this design on paper into a real working database. The absolute bedrock of any table is the primary key. Every single table you create needs one, no exceptions. It's just a column, or sometimes a set of columns, that has a completely unique value for every single row. Think of it like a social security number for your data. It guarantees that we can always find and identify one specific record with zero confusion. So that's great for one table, but how do we connect all those tables we just split apart? That's where the foreign key comes in. It's actually a really simple concept. A foreign key in one table is just the primary key from another table. And that's it. That's the link. This is exactly how we tie an order back to the user who made it, and it's how we enforce all those important relationships we define in our blueprint. And there's one last crucial piece to this puzzle, and it's all about speed, performance. Once our structure is built, we can add indexes. The absolute best analogy for this is the index at the back of a textbook. Instead of flipping through every single page to find a topic, you just look it up in the index and it tells you exactly where to go. Indexes do the same thing for your database. They let it find the data you need at lightning speed, which in turn makes your whole application faster. Phew, okay, we've covered a lot of ground, right? We've gone from the initial idea to refining the blueprint to the actual implementation tools. So let's take a step back and talk about the payoff. Why do we go through all this trouble? Why does this blueprint matter so much? Well, a properly designed database gives you something priceless, a guarantee of reliability. We're talking about something called ACID compliance. It ensures that critical operations, things like transferring money from one bank account to another or finalizing an online order, either happen completely or not at all. There's no in between. It's the ultimate seal of quality, making sure your data stays consistent and trustworthy no matter what chaos is thrown at it. So let's just list out the rewards, the big wins you get from doing this right. First, you use way less storage space because you've gotten rid of all that repetitive data. Second, you prevent those awful data inconsistencies we saw at the very beginning. Third, your entire application just runs faster because your queries are more efficient. And maybe most important of all, you've built a rock-solid, scalable foundation that's ready to grow right alongside your application. So I'll leave you with this one final thought to chew on. Your data, it really is the foundation of your entire application. Everything else is built on top of it. So now that you've seen what goes into making a proper blueprint, the real question is for you, is your foundation built to last?